The yield of the nuclear reaction, this particular one, has maximum magnitudes at the following values of kinetic energy of bombarding neutrons. So the neutrons with these energies are being bombarded, and as a result of this nuclear reaction that occurs, the maximum magnitudes of the yield is noted. So when the maximum magnitude of the yield occurs, that occurs when the nucleus is in transitional phase. So before the products will split out for a fraction of second, everything will be together and everything will be moving together. So that time the maximum energy is being contained by this nucleus. So that's what we mean, the maximum contained energy which occurs at the transition phase. So the yield of the nuclear reaction has maximum magnitudes at these values, and we need to find those corresponding energy levels of the transitional nucleus. So when we represent it in this form, so initially we have these neutrons that have their kinetic energy Ti that is given to us. Then we have a transitional phase, and eventually this neutron and this reaction occurs. In transitional phase, the whole nucleus will have, or you can say whole system will have certain momentum and certain energy. So momentum we will represent by P naught, and energy will be in the form of kinetic energy plus excitation energy. So we have just learned a bit about this excitation energy in the previous problem 6.279. So you can look at that and come back again. So this is how the energy of this nucleus is represented. So it's in the form of kinetic energy and excitation energy of the nucleus. So a transitional nucleus always has some excitation energy, which it loses in the form of splitting of these products. So now that we have the reaction, let's write the energy and momentum conservation for this reaction. And okay, what do we need to find? We need to find this excitation energy E naught. So from energy conservation, Q is final energy minus initial energy. So T naught plus E naught minus Ti. And momentum conservation says PD is equal to P naught. So PD is because we are given in the form of kinetic energies. We'll write these in terms of root 2 md Ti is equal to root 2 md plus mc into T naught. Because in transitional phase, everything is together. So mass of deuteron plus mass of carbon times T naught. So from 1 and 2, we will find the value of E naught. That comes to be this. So our only two variables here are T naught and E naught. So if we just get rid of T naught, we'll get the value of E naught, which comes to be this. So now we know the Q value, which we can get from the excess mass, and we know Ti, which is given in the problem. So correspondingly, we will get this maximum transitional energy or maximum energy of the nucleus, that comes to be this much. And for the other deuterons, we will get some. So of course, if the energy of the deuteron is more, the energy of our transitional nucleus should also be more. Hence we get our answers. All right.